So for this video tutorial, we're going to be speaking about chemical formulas and the different ways that we represent compounds when we're speaking about organic chemistry. In this case, we have methane, which is one of the simplest compounds in organic chemistry. It's a hydrocarbon that has only one carbon atom and 4 hydrogen atoms. And this formula that we have right here is a molecular formula. If you remember from other chemistry courses, molecular formulas give us very few details about what we're talking about. They only give us the type and the amount of atoms present, but they don't really give us any more information. So here, this is a molecular formula. It's just telling us 1 carbon for 4 hydrogens. However, there are other types of formulas. The first formula I'm going to talk about is the expanded structural formula. And in this expanded formula, like its name is shown, we have all the atoms laid out and in their specific locations. So I have carbon in the middle. And if we remember that carbon can only make 4 bonds, we represent the single bonds with these lines. We're going to arrange our hydrogen around the carbon atom, which is the central atom. Then we're going to move on to something which is my condensed formula. The condensed structural formula clusters all the atoms around a central carbon atom. So in this case, for methane, it's the same as a molecular formula. But let's make another quick little example with ethane. Ethane, its molecular formula is C2H6. Which would mean that its expanded structural formula, we have 2 carbon atoms, and around these atoms, we have their respective hydrogen. But once we condense it, we look at each of these carbon atoms, and we look to see what's around them. So this carbon has hydrogen attached to it, and then this other hydrogen is attached to this carbon in the middle, also this hydrogen, and this is what we have. So once we condense it, our condensed formula is going to be CH3 dash to indicate that single bond between the carbon and the other carbon, CH3. You might also find it represented in other books in verse to be a little bit more precise, because effectively what's bonding is a carbon. So these two are the same, but they're telling us what's around each carbon atom. Once we step away from these formulas, the last formula I want to present here is the line angle formula. In which the rules are that you represent carbon with one of the dots of the vertices of this hexagon, and we connect the lines, and the lines, which are the actual sides of the hexagon, represent the bonds. So in this case, I take one dot and I connect it to the next, and this is representing the whole ethane molecule, right? So this is ethane, and this is ethane as well. And how can we prove it? If we think that each of these is a carbon atom, we have to see how many bonds it's making. So this carbon is bonding once with this, so that means it's implicit, and this is just a little method, that we have 3 hydrogens floating around here. And then here on this side, we have another 3 hydrogen atoms, and we can finally conclude that we have this same molecular formula, which is C2H6, C2H1, 2, 3, 4, 5, 6, and we have a line angle formula. I lied to you a little bit. There's another formula type, which we could call the carbon backbone. And the carbon backbone formula is characterized by only telling us the position of the carbon atoms and the bonds that they're establishing within them, between them. But we can also do this, what I call cherry method, to figure out if we're doing fine. This carbon is bonding once over here, but it also has 3 hydrogens that are implicit. And here this carbon is also with its 3 hydrogens that if we convert again, this is going to turn into C2H6, ethane, or CH3, CH3. Now, let's look at an example that could be a little bit more complex. And I'm going to start in reverse, maybe, with carbon backbone, for example. So here I have a carbon backbone. And in this case, since we have a cyclic molecule, because all the carbons are closing in together into a ring, we're going to try to convert it into the other formula types. So there are a few ways to do this, but let's see. Carbon backbone, and then we analyze each carbon. This carbon is making 2 bonds, so that means 2 hydrogens are floating here. This carbon is making 2 bonds, so there's means 2 hydrogens are here. This carbon, 2 more hydrogens, and this carbon, 2 more hydrogens. And then from this one, we can jump on to the next type of formula, which is my expanded formula. So I copy the same grid, but now I turn those cherries, like I like to call them, into hydrogen atoms. And this gives me effectively a expanded structural formula. So expanded structural formula. Now, again, if I want to condense this formula into condensed structural formula, which shows me the arrangement and the clusters of the atoms, I look at each group, and here I'm going to take a red marker, and I don't forget about the bonds going on between the carbons, and I say, top corner, I have CH3, which is bonding to the other top corner CH3, and which is bonding down to another CH2. I'm sorry, I made a mistake up here. CH2, CH2. Then we connect to another CH2, and then we close up over here. So then these 3 are equivalent, and we just finished our condensed formula. Condensed structural formula. Then, from this one, we can just infer, and we can make 4 dots to make our line angle formula. 1, 2, 3, 4. We connect the dots like if this was a children's game. And this is the same formula, only this is line angle. And we just compare and we see 1, 2 bonds, 1, 2 hydrogens, 1, 2 bonds, 1, 2 hydrogens, 1, 2 bonds, 1, 2 hydrogens, 1, 2 bonds, 1, 2 hydrogens. So we're still keeping the same stability. And now, last but not least, for our molecular formula, we know that there are 4 carbon atoms. And these 4 carbon atoms manifest as C4. And then H, we count our cherries. 1, 2, 3, 4, 5, 6, 7, 8. H8. And that concludes this tutorial with the creation of our molecular formula. That only gives us the specific amount of atoms, but not their location. And that's it. Thanks.